Okay, so is everybody here? We're on page 531, practice problems number 1, 2, and 3 on chapter 17-1. Okay, so before we do anything else, I want you to take a look at this chart. Okay, the experimental data for hydrogen and chlorine becoming, what is this? HCl, which is hydrochloric acid, right? So check out the numbers. I want you to see if you notice anything strange or anything interesting. Right? Yeah, okay, so check this out. HCl at 0 seconds has how much? 0, right? Why do you think that is? It's because no reactions happen, right? And so if nothing's happened, how much product do we have? Nothing, right? That's exactly why we would expect nothing to be here. And what's the direction of the arrow? Going to the right, right? Now is it like a double arrow, one side and the other? So it's only going one direction with this reaction. Exactly. Okay? Now, let's take a step back and let's talk about rate. Okay? If I said, and I'm just going to write this on this paper, so don't write this on yours, but let's say that, let's pick somebody. Let's say Nazim runs 2 miles in, I don't know, he runs 2 miles in, let's give it, I don't know, 14 minutes. He's a quick dude, right? Okay, so if he runs 2 miles in 14 minutes, you notice how I put the 2 miles on top? And I put the minutes on the bottom? Why did I do that? Exactly, like my units in this case are going to be miles per minute. Okay, now you notice how time is on the bottom? If we have time on the bottom, it turns it into that rate. So we do like, you know, with a car, usually we measure it miles per hour, right? Now that P, all that is going to be this line right here. So it's miles per hour, right? So far so good? Okay, so when we talk about rate, we go miles per hour or miles per minute or something over time, right? So the key idea is something goes here on the top and it's going to be over time on the bottom. Okay? So with that in mind, let's take a look at these problems. Okay, so number 1, let's go ahead and have Alan read that for me. Okay, so let's take a look at the units that they said, right? So it says moles of H2 consumed per liter per second. Right, now first of all, we see H2. What is H2 in our reaction? It's okay, so it's hydrogen, but it's a what? It's a reactant, right? It's on the left side, so it's a reactant. So are we going to expect there to be more and more H2 as the reaction goes on, or less and less? Less and less. Why? Because being consumed is turning into product, right? Our HCl product. Okay? So if we're looking at H2, it says per liter per second, right? So let's go ahead and write down number 1 up here. So we've got number 1. And they're asking for moles per liter per second, right? Let's finish that. Now here's where the trick comes in. Do you remember our big M, the molarity? Okay, so your molarity, do you remember, was equal to? Moles divided by what? Liters, yep, exactly. That's going to be super important. because what we're going to look at with this rate, right, it's going to be concentration over time. We're always going to have delta M, right, big M, molarity, your change in molarity over your change in time. Now you notice how my T has a tail? You're going to want to start adding these tails to your T's. Why is that a good idea? Yeah, so you don't mistake them for a plus, right? You take this away, it's just delta plus. And so if you add a T, you know that's going to be T for time, right? Add that tail, because capital T would mean something else. So use the little tail, trust me, it'll help in the future. Okay? So we've got delta M divided by delta T, so change in concentration divided by the change in time. Let's take a look at the data we have. Okay, so if we look at our time, remember, when we're finding delta T and delta M, we have to use final minus initial. So what you end up with minus what you started with. So in terms of time, let's do time first. I'm going to draw this little line here. If we start with final, right, final was 4 seconds. So we'll go 4 minus, what did we start with? 0. So 4 minus 0 on the bottom. And then on the top, if we're looking at H2, that 4, they ended up with 0.02. Alright, and you started off with, so minus 0.03. Okay, so far so good? Awesome. So let's put an equal sign, and if you don't have a calculator, you need to secure one somehow. We have extra calculators up here at the front, or there's probably some in your desk cubbies. But I'm going to go ahead and do this. It looks like negative 0.01 divided by 4. And then plug this into your calculator. Plug it in and then check up here to make sure your answer is correct. Now, why is this a negative? Okay, yes, exactly, right. So, thank you, Captain Obvious. We have a negative, but what are we going to? Why would we expect a negative there?
Because that's what
Yeah, exactly. Like, would we expect there to be more and more hydrogen? No, because we're losing it, right? And at what rate are we losing it? At this rate, right? And you go, okay, well, what is this? Well, right now, let's take a look. It's, what are our units? We have delta M and T, right? So that's molarity divided by, teams, we had seconds. Yeah, go outside, count to 100. Come on. Be careful with our language, sir. Okay, 0.0025 molarity divided by seconds. And what is it asking us for? Moles per liter per second. Well, what does your big M equal? Equals moles over liters divided by seconds. So if you have moles per liter per second, moles per liter per second, and then you can condense it to be moles per liter times second. Now, do you see how I did this? Okay, so let's think about this. Moles is being divided by liters. right? Which is being divided by seconds. So if you were to go on your calculator and you were to say, hey, if, again, this is math, so I'm not going to go too far into it, but I want to make sure you at least kind of get this point. If you have, again, we should probably just pick a number. If we picked a number, we put it here as moles. We divided it by a number of liters, and then divided it by seconds. It's the same as if you multiplied liters times seconds, and then divided moles by that number right there. Okay, because all you're doing, think about this. Your liters is just slipping down here to your seconds. Okay? How are we feeling? Okay, so it's like, okay, so like this, right? If we have 1/2, right? So if I had 1/2, and then, here we go, 1/2 divided by 2 is what? 1/4. How did you get, so this equals 1/4, right? But how did you get this 4? You see, you go 2 times 2, 1 divided by 2 times 2 is 4. Alright? Does this make sense? So, yeah, dude, math is amazing, right? And so, moles divided by liters times seconds is the same thing as this. Okay, good. I'm glad we did that, so that makes more sense. Perfect. Okay, so this is our final answer. You don't have to have all of this stuff. I just want to make sure you have your number and your units. Alright, but how are we feeling about it so far? Doing alright? Okay, let's try another one. Let's go to number 2. Okay, so number 2, calculate the average reaction rate expressed in moles of what? Cl2 consumed per liter per second. So it seems like it's the exact same thing we just did, except with, yep, exactly, with that. So let's set it up. Okay, so now we're going over here. So I got my change in molarity. It's a delta, I promise. Divided by our change in time. Now we started off, remember it's final minus initial. We ended up with 4. We started off with 0 in terms of time. Molarity, we started off with 0.05. And we we ended up with 0.04. Can use a calculator. This should look pretty familiar. It's the exact same thing. Equals, there we go, 0.0025 moles per liters per second. Try, yeah, so 0.04 minus 0.05 is going to be negative 0.01. Right? And again, why would we expect this to be negative? Because it's a reactant, and so we expect it to go down as it becomes the HCl. Cool. Alright, now do you see how easy this is?
Yeah.
You just got to go step, 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 and boom, you got it. Let's try number 3. I want you to do this one on your own. So give it a try. I'm going to do it up here, but a little bit slower. I'm going to give you a little head start. Good luck on the game today. Okay, so again, do this on your paper. Don't look up unless you need help. Oh, okay, so this is going to be a change, right? So watch. If you do it with this one. Do for number 3. You notice how your number is going to be... No, go do it first and then I'll show you. You'll see. Your number is going to be positive instead of negative. And the reason why is because you're adding more product, As your reactants react, you get more product. So your reaction is going to be, your rate is going to be positive. Okay? So, is everybody getting 0.005? No, you're good. Cool. All right. How are we feeling about this? We're feeling smart. I like that. I like that answer. Okay. Now, of course, as any good teacher will do, we get the basics, and then what do we get to do now?
Ramp it up.
Let's ramp it up a little bit. Let's see how far we can push this. So, put this off to the side, and let's turn to page, let's go, 547. So, page 547. Okay, now this one, we're going to be using the example problem above to help answer these ones. Okay, so let's go ahead, before we do anything else, I want you to take a look at the reaction. Okay, so what's going on with this reaction? Yep, so we have how many moles of nitrous oxide, NO? We got 2 moles, okay? How many moles of H2? Well, we have 1, right? We have 1 mole of H2. And that's becoming 1 mole of N2O and 1 mole of H2O, right? So in this case, though, let's think about this. If I am trying to figure out how fast somebody goes, one thing I could do is measure how long it takes them to go from start to finish, right? But if I'm measuring how fast these things turn into, like your reactants turn into your products, I could do one of 2 things. I could either measure how fast I get rid of these, right? Or I could measure how fast I get these, exactly, that these are made. Okay, so there's 2 ways I could do that. What we're going to look at is measuring your concentration of your reactants. Why? Because it's usually a little bit easier. Because you the one that mixed these reactants together, and so you know what reaction, how many molars you put in. It's usually a little bit easier that way. Okay? So, again, keep in mind how many moles are in each one, because that's going to come back and be really important later. Okay? The other thing I want to point out, and this is kind of new, so don't freak out, we'll get there, but it says there's a rate constant of 2.9 times 10 to the second. Right? Now, when it says rate constant on your paper, I want you to write down, so we'll draw like a line if you have this one, the stuff that we did earlier. I want you to draw a line underneath it. And I want you to write down, put K equals rate constant. Okay, your K equals rate constant. Alright, everybody got that? Sweet. Okay, I'm going to move to a separate sheet of paper just so I can keep making my numbers big. Okay, so we know what the rate constant is, so I'm going to put K equals, right underneath it, even though I just wrote rate constant, I'm going to put K equals 2.9 times 10 to the second. Which really, if I move the decimal place over 2 times, right, 1, 2, that's 290, right? So that's my K. K equals 290. Alright. The next thing I want to point out is going to be our rate law. So if you notice, right above where I have this sheet of paper, this is our rate law. So go ahead and write that down. Put rate equals K times the concentration of NO, and there's squared times the concentration of H2. Now, why do you think that we squared the concentration of NO? We had 2 moles, right? So you remember up here, we've got 2 moles of NO, so we have twice as much concentration of these. And how many moles of H2 do we have? 1, right? So you could think of this as being H2 to the 1 power. Okay, so when we're doing rates and rate laws, if you have a coefficient in front of yours, so if you have twice the number of moles, you're going to put the 2 up to the power. What happens if I would have had 3 NO? I would have cubed it. I would have put 3 as the power I would raise it to. Exactly. Okay, so this is the rate law for this reaction. Now let's see if we can use it. Okay, let's go down to the question. So Megan, could you read me the question starting with use the rate law? Okay, perfect. Now, you notice how it gives us the concentration of NO, and it gives us the concentration of H2. For our equation, we just put that number in here, and put that number in here, and do we know what K is? Yeah, K is equal to 290, so really all we have to do is just fill in our unknowns, right, our variables. K is 290. Our concentration of NO was 0.005. Square that. And H2 is 0.002. And that's going to be equal to our rate. So all you got to do now is just take your calculator and plug this in. The trickiest part is going to be making sure to remember to square just this one. Okay, so give that a try. And I'll do that with you. I'll put my calculator right here. Okay, so I'll go 290. So your answer should look something like this. Okay, now let's think about units. What are my units going to be? Well, we're talking about rate, right? So it's got to be something per, exactly, right? So something over time. Now what are we measuring? Down here, it's molarity, right? That big M. So what did we get for our last ones? We ended up getting rate equals moles divided by liters times seconds. So you're actually going to be getting the exact same thing. Yeah, it's going to be basically default. Yep, that's a good way to think about it. Alright, good luck with your meat. Okay, how are we doing? Alright, yeah, what's up? On your calculator, okay. Let's try it on a separate calculator, right? Okay, so we type in, so do this with me on yours. And I'm probably going to do this the wrong way first on this one, but let's see. So we got this. You know what it might have done? Okay, we'll see it. Here we go. So we got 290, and I'm going to just go ahead and multiply it across right now, times 0.002, right? So I'm getting, right now this times this is 0.58. Right? You getting that number? Okay, cool. So now it's, I got 0.005 squared times 0.58. So I'm going to go ahead and clear it. Go to 0.005 and then put exponent 2. And that's actually the wrong way to do this, so I apologize. 0.005. Let's see if I can find a caret. I might need to put mode on here. Good luck with the game. I'm not going to be at this game. No, I go to almost all their games. Okay. So there we go. So that's 2.5 times 10 to the, so we go 2.5. 5, so 1, 2, 3, 4, 5. Point 0.005 squared. What would you get? Did you get 25 or 2.5? Okay. If you got 25, look, at 25 to the negative 6 is going to be the same thing. That just moves the decimal point over 1. See how that works? Okay, and then you multiply that times this, and you should get the same answer. But we can do a calculator thing. Do you get it? Mhm. Cool. Good. Okay. Glad we got that worked out. Let's go to the next one. 25. Now I'm going to do this one with you, and then the last one, 26, you're going to be doing on your own. So let's track. First things first, I put down my equation, right? Rate equals K times the concentration of NO squared times H2 squared, or excuse me, the concentration, this is H2 down there, to the first power. Now I just fill in the numbers I have, right? 290 for K. My NO, though, is going to change to 0.01 and squared. H2 is 0.00125 to the first. Okay, so try plugging this into your calculator. Alright, we're getting something like 3.6 times 10 to the negative fifth. Cool. One thing I do want to point out, things to notice, as you get more and more familiar with it, you'll see this. But if you compare the concentration you have of NO, nitrous oxide, with the concentration you have of hydrogen, look, you got 0.01 and you've got 0.00125. So you have almost 10 times more NO than you do hydrogen, right? So, but if you notice, what do we have to do to this concentration? We had to square it. And if you take 0.01 and you square it, it turns out to be a much smaller number, right? And that's because we need twice as much NO to interact with our H2. So even though we have this massive amount of NO, it can only be reacting with this much H2. So that's going to limit that. And we'll talk about that later. But give number 26 a try. I want you to try this one on your own. Do the same steps we did with numbers 25 and 24.